Hello everyone. Today we are going to discuss about the topic that is pH buffer and isotonic solution. In the previous video, we have to see about related to pH. Into today's, we have to discuss about the related topic that is buffer, the part 2. So first of all, that we have to see the definition. What is buffer solution? So the buffers, we can say, is a compound or the mixtures of compound due to their presence, their compound which resist the changes in the pH after the addition or upon the addition of the small amount of alkali or acid into the solution. So that is a buffer solution, or otherwise a solution whose pH is not much altered by the addition of small amount of strong acid like hydrogen ion or strong base like hydroxide ion, OH minus ions, is called the buffer solution. So that buffer solutions that maintain the pH, that by neutralizing the small amount of that we have to add the acids or base. So the acid must be present to react with the OH minus, any OH minus that we have to add, and the base must be present to react with any HCO plus that we have to add. So in that, what is the need? So why we have to go for that buffer systems? So buffer solutions that are very much important in biological system as well as in pharmaceutical field, in medicine field. So because most of the biological reactions and the enzymes that need very specific pH for particular their function that work properly. So that's why that pH dependent that systems reactions are there. So specific pH, that particular function that properly work. So in that pharmaceutical formulation parts are often based on the buffer to control the pH. Buffer system we have to maintain it, that helps to minimize the drug degradation, that decomposition part. So in that buffer system, that is necessary to maintain the pH of pharmaceutical solution or any pharmaceutical preparations if they are stored for a longer period of time, because due to the long time storage of that pharmaceutical or that solutions, that may be a chance with the time durations, maybe a change in the pH may be altered that towards the acidic if solution comes in contact with the air. So that leading to the absorption of that CO2, so it slightly go for the acidic. In the opposite side, in on the other end, that we have to see if the solution is stored in a glass bottle based on the container. So glass bottle packaging parts in the container, so the alkaline impurities that form with the glass, means leaching from the glass material, so might also alter its pH. So that's why, so therefore we can say that the pharmaceutical solutions are buffered by the buffer solution, that which is capable of maintaining the pH at a constant value when small amount of acid or alkali that is added to it. For that, there is a pharmaceutical base like similar like biological system. For the example, so pH of blood, so that lies about 7.3, around 7.35. So if these values falls below the 7, pH 7, so it occurs acidosis, or if it is rises above 7.7 like that, so alkalosis are there. So both the case, the results are fatal. So it dangerous effect that we have to see. So blood contains a buffer system, the plasma and erythrocytes, so that maintain the acidity at the right level. So that's why that require the buffer system. So when we have add acid or base in that water part, so the pH going changes. For example, the pH 7s are there for the water. So if add the HCO plus OH minus like that, so it changes drastically from 7 to 4, 10.5 like this. So changes are there when we have to add acid or base in the water part. In buffer solutions, the pH is maintained, slightly difference are there. If pH 7 is there in the buffer solution, so pH does not change when we have to add a small amount of acid or base. So they have to slightly change from 7 to 6.9 or 7.1, 7.2, 6.8 like that. So in that buffer solution, the terminologies are there like buffer action, buffer capture, resistance to a change in the pH. So that is the buffer action. The effect of buffer solution, the action, that resistance does not go for the change in the pH, and the amount of the acid or base that required to produce a unit change in the pH in the solution. So that is known as buffer capacity. So the buffer solution, that capacities are there above that concentration that may change in the pH. So that amount, that is the capacity of that buffer solution to resist the pH or does not change in the pH parts are there. So typically the mixtures of in the buffer solution, mixture of weak acid and the salt of its conjugated base, otherwise or weak base with its salts of conjugated acid. So that is a combination of, that we can say that the combination of weak acid to its salts. So it may be acid buffer, we can call acidic buffer solution, and when we say that the pH is less than 7. The example, acetic acid plus sodium acetate. Similar like for alkaline buffer solutions, combination of weak base and its salts with its salts conjugated acids. So their pH is greater than 7. A mixture of ammonia solution and ammonium chloride solution. Characteristics of buffer. So buffer have a definite pH values are there. pH values of buffer does not alter, either we have to keep for longer period of time or we have to go for dilution. So any changes are there, so that does not differ their pH values. And pH values of buffer is very slightly altered by the addition of small quantity of acid and base. So these are some characteristics of the buffer system. So that already we have to say the types of buffer in that. So if acidic buffers are there, the solution of mixture of weak acid with its salt, means conjugated strong base. So that example, acetic acid plus sodium acetate. So weak acid is acetic acid plus their salt. And similar like the basic or alkaline buffers system solutions are there. So in that combination of weak base with its salts, conjugated acid, strong acid. So mixture of ammonia solution with ammonium chloride solution. So in that the ammonia, the weak base are there, ammonium hydroxide and ammonium chloride, then salt forms are there. Then next the buffer actions or buffers, how they can work. So mechanism. So the resistance of buffer solutions to a change in their pH. So that already we have to say that it is a buffer action. So in that both the types of buffer, acidic buffer and the basic buffer. So we have to say mechanism of actions for acidic buffer. So in that, suppose buffer system of, here examples they are given for the weak electrolytes like acetic acid and the strong electrolytes, that is the salt form of that salt form, sodium acetate. So in that case there will be a large concentration of the presence, that is sodium ion, Na plus ion, there are acetate ions, CH3COO, Na minus or CH3COO minus, and undissociated means the acetic acid molecules, the weak electrolytes. So when conditions are there, when we have to add, acid is added, in that acetic acid and sodium acetate mixture solution buffer system. So if strong acid, that we have to add hydrochloric acid, that we have to add, suppose example, in a buffer system. So change that will occur. So the hydrogen ions that yield by the HCl are quickly removed as the unionized acetic acid, and the hydrogen ion concentration in this system is therefore only slightly affected, because acetic acid that produce after that H plus Ca3COO minus, so it creates the Ca3COOH acetic acid molecule that produce the weak base as compared to hydrochloride, so that maintain the pH. When the base is added, if we have to add NaOH, previously we have to see if in that system acetic acid and sodium acetate buffer system we have to add acid, so that yield the undissociated acetic acid molecules. When we have to add base like strong base NaOH in that buffer system, so what happens? So the hydroxyl ion, so that from NaOH, Na plus OH minus, so OH minus is react with the acetic acid molecules, the Ca3COO minus plus H plus, so the H plus OH, so water, so hydroxyl ion yield by the NaOH, therefore that removed quickly as a water molecules. So the supply of the hydrogen ion H plus as that needed for this purpose or for the reaction, that is constantly that is provided by the dissociation of acetic acid. So when NaOH that we have to add in that system, so NaOH going for dissociate Na plus OH minus, and that yielded hydroxyl ion that react with the acetic acid dissociation from that Ca3COO minus plus H plus. So from that dissociation of acetic acid, the hydrogen ion that react with the hydroxyl ion of that NaOH, so that convert into the water molecules. So that is the effect of that buffer action or buffer system. Similar, like we have to see the buffer action or mechanism of action of in the alkaline buffer or basic buffer. So for that, the examples we have to take the weak electrolytes, ammonium hydroxide, that is weak base, and it solves the ammonium chloride, NH4Cl, that is strong electrolyte. So here in that case, so there will be a large concentration of NH4 plus ion, chloride ion, Cl minus ion, and undissociated ammonium hydroxide, NH4OH molecules are there. Similar, like previously we have to see the mechanism of actions of or buffer action of acid buffer. Similar, like here we have to see the examples. So when we have to add the acid, that we have to add in that case the hydrochloride acid, strong acid, that we have to add it into the NH4OH, NH4Cl buffer system. So what happened in that? So in that the HCl go for dissociate, H plus ions are there. They have to react with the dissociation of ammonium hydroxide, NH4OH. In that case, the OH minus hydroxyl ion that react with the H plus from the hydrochloride. So water molecules remove. So here in that, so hydrogen ion that yielded by the hydrochloride are therefore removed as a water, and the supply of the OH minus is constantly provided by the ammonium hydroxide dissociation. Similar, like second, that we have to see if we have to add, instead of acid, that we have to add the base, strong base that we have to add in that buffer system, NH4OH, NH4Cl, strong base that we have to add NaOH. So what happened in that part? So in that, so NH4OH that dissociated NH4 plus and OH minus, and NaOH go for dissociate Na plus OH minus. So now what happens? So the hydroxyl ion from the NaOH molecules, the OH minus is there, that yielded by the NaOH dissociation, and therefore that react with the dissociated of NH4OH in that ammonium molecules, NH4 plus, that react with OH, so that convert into that weak base NH4OH. So the hydroxyl ion yielded by the NaOH that are quickly removed as the unionized ammonium hydroxide, and the pH of the solution is only slightly affected. So this is a mechanism action of buffer or buffer system in both the case, in acidic buffer or basic buffer, that we have to see. The next terminology, that is buffer capacity. So what is that buffer capacity? So it is defined as the number of moles of an acid or base that is required to be added to 1 liter of the buffer solution, so as the change its pH by 1. Or we can say that the buffer capacity of a solution is a measure of its magnitude of its resistance to change the pH in addition of an small amount of acid in or base. So the buffer capacity is referred as a buffer index, buffer value, like that, buffer efficiency or buffer coefficient, and the buffer capacity is represented by the symbol that is like small b beta, that may be also defined as if the ratio of the amount added of strong acid or base to the small change in the pH that brought by the addition. So that is also that buffer capacities are there. So that represented the equations. The buffer capacity is equal to delta B or delta A upon delta pH. So where that delta, that it is usually meaning the finite changes are there with that process, change in that pH, and the delta B is the addition, small amount addition, that small increments in gram equivalent or liter or strong acid or base that we have to add to the buffer to bring about a change of the pH. So that is the ratio that we have to call as a buffer capacity. So the amount simply we can say that the amount that we would require to slightly change the pH of that solution or buffer. So that is represent buffer capacity. So according to that equations, above equation, that we have to see that buffer capacity is equal to delta B upon delta pH. So that we can say, so the solution have a buffer capacity of 1 when 1 liter of it requires 1 gram equivalent of a strong acid or base to change the pH by 1 unit. So therefore the lower the pH change in a solution when acid or base is added, so greater the buffer capacity than with the vice versa. So greater the buffer capacity, so less the pH changes upon addition of H plus or the OH minus. So choose a buffer whose pK is closely to their desired pH. That we use. So buffer capacity, they depend on we can say there's a two factors essentially. One is the ratio of the salt to the acid or base, that dependent buffer capacity, and second is the total buffer concentration. So buffer capacity, we can say that is not a fixed value. So it depends on already we have to say the ratio of salt to the acid or base or total buffer concentration. So it depends on the amount of the base that we have added. For most of the pharmaceutical preparation solutions, buffer capacity, the ranging between, we can say that it around 0.01 to 0.1. So are usually adequate. So more than 0.2, we get less the buffer capacity solutions are there. So buffer capacity must be large. We can say that the greater to enough to maintain the pH of the product for reasonably long storage time, long duration time. So change in the pH of the product may be result from the interaction of the solutions, we can say component with each other in the preparations, or maybe interactions with the container like glass, plastic or rubber. So that's on the other end, that buffer capacities for the ophthalmic and parenteral products should be low enough to allow the rapid product readjustment and physiological pH that upon the administrations. So so we can say choose a buffer whose pK, the ionization concentration, is closely to the desired pH. So pH should be within pK plus, or we can say plus or minus 1. The next, the buffer equations. So the buffer equations, the pH of the buffer solution and the change in the pH that we have the addition of that acid or base, that is calculated by the use of buffer equation. So that is, we can say, the Henderson-Hasselbalch equation. So in that history, so Lawrence Joseph Henderson that wrote an equation in 1908 that describing the use of carbonic acids as a buffer solution. Then further, the Karl Albert Hasselbalch that later that re-expressed that formula in the logarithmic term, and that results become that equation combine that Anderson-Hasselbalch equation. Two separate that equations that obtained for each system, each type of buffer, for acidic buffer and the basic buffer. So buffer equations is developed based on the effect of salt on the ionization of that weak acid, and when salt and acid have a common ions are there. So in the both we have to find out the buffer equation for weak acid and its salt. It means the buffer equation for the acid buffer. So in that case, the acid is known as a proton donor. So the pH of that acid buffers that can be calculated from the dissociation constant, that Ka of the weak acid, and the concentration of the acid and their salt that is used. The dissociation expression of that weak acids can be represented, that we have to say as a Ha is equal to H plus and A minus by applying the law of mass action. So Ka is equal to H plus A minus upon Ha minus. Then we can write down like that, H plus is equal to K into Ha upon A minus, where K is the dissociation constant for the acid, that is Ha. Now of the addition of salt to that acid, that we have to add the salt to that acid, so the dissociation constant get disturbed by the addition of that salt, and that which provide the A minus ion. So the degree of that dissociation of an weak electrolytes, so is example like acetic acid, so it's suppressed by the addition of another strong electrolytes like sodium acetate that containing a common ion. This is term which is called as a common ion effect. So a weak acid is slightly dissociated, and its dissociation is further depressed by the addition of that salt, so which provide common ion effect, that is A minus ion. So as a result, the equilibrium concentration of the unionized acid is nearly equal to its initial concentration of acid. So the equilibrium concentration of A minus that we can assume to be equal to the initial concentration of that salt that we have to add, since it is completely dissociated. So therefore we can represent A minus by their salt concentration also. So if acid is weak and slightly ionized, then Ha is represented as a total concentration of acid. So here we can write down Ha is acid, and common ion concentration A minus is result from the salt. So that by the H plus is equal to Ka acid upon salt. So that equation that we have to write down. Then we have to take the log from both the side. So log H is equal to log Ka plus log acid upon salt, or Ha upon A minus, like that we have to write down. Then multiplying both the side negative sign, so minus log H plus is equal to minus log Ka minus log acid upon salt. Now we can say that as a definition of pH, we can say pH is equal to negative logarithm of hydrogen ion. So pH is equal to minus log H plus, and minus log A is equal to our pK, dissociation constant. So we can write down the equations for Anderson-Hasselbalch equation. This is called, so pH is equal to pK plus log salt upon acid, and also write down like pH is equal to pK minus log acid upon salt. So opposite like that, salt upon acid. So positives are the pH is equal to pK plus log salt upon acid, or pH is equal to pK minus log acid upon salt. So this is called the Anderson-Hasselbalch equations. It helps in calculating the pH values of that buffer solution if the concentration of acid as well as the salts that we can known. Similar like this is, we can find out the buffer equations for weak acid and its salt. Similar like we have to go for the buffer equation for weak base and its salt. So same that we have to go for it, like that equations are there. And ultimately lastly we have to find out, instead of pH is equal to pKa minus log plus pH is equal to pKa plus log salt upon acid. So that time we can find out POH is equal to, for the base, weak base, so POH is equal to pKb plus log salt upon, instead of acid, that base we can find out. So that is the Henderson-Hasselbalch equations for weak base and its salt and weak acid and its salt. So now the significance of that Henderson-Hasselbalch equations. So that is, for basic buffer will give POH, and so pH can be calculated from that. So pKw is equal to pH plus POH, or we can write down pH is equal to pKw minus POH. That pKw, that is 14. If the pH is equal to 14 minus POH, if we can find out, if know the POH value, so we can find out the pH. So that is the significance of that equation. Next is the buffer in pharmaceutical and the biological system, the applications or significance that we can say that. So in that, the buffer in the biologic system, so in that the blood. So blood is maintained, already we have to see that examples, so pH around 7.3 or 7.4. So their pH should be maintained by the primary buffer and the secondary buffer. So that maintained by the primary buffer in plasma and secondary buffer in erythrocytes. So the plasma that containing the carbonic acids, bicarbonate and acids, alkali sodium salt or phosphoric acids. So like that the buffers are there. And in plasma protein which behave as acid in blood, and that combine with the base and so act as a buffer. And secondary buffer in erythrocytes. So two buffer system that consist of that, the hemoglobin or oxyhemoglobin and acids, and the alkaline potassium salt of phosphoric acid. So in that that is biological buffer system. The example in that blood. Secondary, the lacrimal fluid. So the pH of the tears or lacrimal fluids is also similar, like 7.4. So they have found to have great degree of buffer capacity, that allowing the dilutions of 1 gem 15 with neutral distilled water. So its pH range is slightly, that we have to say that maintain. So in that the pH increase rapidly when sample is removed from analysis because of loss of carbon dioxide from the tear fluids are there. Similar like in the urine also. So urine of normal, we can say that the range for the adults is around 6 and the range is 4.5 to 7.8. When pH of the urine is changes, if below normal values, so the hydrogen ion are excreted by the kidney. And if pH above the 7.4, so that the hydrogen ion are retained by the actions of that kidney. So that maintain the buffer system in biological part in the blood, lacrimal fluid and the urine. In pharma point of view, in pharmaceutical part, the pharmaceutical buffers are there. So buffer solutions that is used particularly in the formulations of ophthalmic solutions. So many buffer systems are there. So in that is, as per Gifford, when we mix proportion of boric acid and monohydrate sodium carbonate, so that yield the buffer solution with pH range of 5 to 9. That is, many buffers are available nowadays. We can prepare any one, like second Sorensen, that proposed the mixture of salt of sodium phosphate for buffer pH range of pH 6 to 8. The sodium, the other than buffer system suggested by the Palisades consist of boric acid, sodium borate and NaCl, and that used for ophthalmic solutions with pH around 7 to 9. In all the case, sodium chloride we can use to maintain the isotonicity in the for ophthalmic preparation. Other than the buffers of Clark and Lubbs that were determined at 20 degrees Celsius, determine at 25 degrees Celsius that the Clark Loves mixtures and their pH ranges they are given. If we can prepare pH 1.2, so HCl and KCl like that, the things are there for the many buffer systems that we can prepare by any of that formula. So now the preparation of the standard pharmaceutical buffer solutions. So that type of the criteria conditions that we have to know it. So that initially that we have to select the weak acids that having a pK that nearer to that pH at which the buffer is to be used to ensure the maximum buffer capacity. So that we have to consider. Then calculate the ratio of the salt and the weak acids that required to obtain our desired pH. So buffer equation that we have to use for calculating that part. Consider the individual concentration of buffer, salt and acids that need to obtain suitable buffer capacities. The concentrations 0.05 to 0.5 molar is usually sufficient, and buffer capacity we already have to say the range from 0.01 to 0.1 is generally adequate. Before we have to go for it, the preparation of standard buffer, we have to see the availability of that chemical based on their selection, sterility of that final solution required, stability of drug and the buffer on the aging, the cost of that materials, chemicals, and freedom from the toxicity should be considered for the use of that buffer solution system. Because examples they are given, so the borate buffers that we have to use, so because of its toxic effect, certainly cannot be used to stabilize the solution to be administered orally or parenterally. And lastly, to determine the pH and buffer capacity of that completely buffer solutions by using the reliable pH meter. Here some examples given for the standard buffer solution. Commercially buffer solutions are there most widely used. In that we have to go for the preparation in pharmaceutical field, in the preparation of pharmaceutical solution or any the dosage forms for liquid dosage form like that. The pharmaceutical preparations, in that the hydrochloric acid buffers are there, acid phthalate buffers are there, acetate buffer that we have to say, then the citrate buffers are there, phosphate buffers that most widely used, and they are given their compositions, their pH range, and where we have to use that given in that table. Other than that, carbonate buffers are there, triacetate buffer, triborate buffers. So many things are there most widely used: the acetate buffer, citrate buffer, phosphate buffer, and hydrochloric acid buffer. Around that we have to go for the pH of from 1 to the 10 like that. Lastly, the applications of the buffer system or buffers are there. So in the pharmaceutical point of view, in the pharmaceutical preparation of formulations, so buffer is used generally for the pharmaceutical solution to control the pH of that formulations or the product, and that control of that pH that affect into their solubility. pH based solubilities are there, pH based stabilities are there, so that counter the stability problem. pH based absorption probability problems are there. So that's why that buffer system that helpful in that preparations, like parenteral preparation, in ophthalmic preparation, ointment and creams are there. So to adjust the pH of drug and medicines in order to minimize their drug degradations that improve the patient comfortness are there. In injections, acetate, phosphate, citrate buffer that you have to use. So in that parenteral that we have to see, so the large deviation of pH in case of parenteral preparation may be caused serious damage, injuries, consequences are there. So the most commonly that we have to use that acetate, phosphate, citrate or glutamate, the buffer systems we have to use. In similar like ophthalmic preparation, that including any conventional ophthalmic preparation like eye drop, eye solution, eye lotion, ointment like that. So we have to maintain that pH with the lacrimal fluid pH. So buffer system that we have to use in ophthalmic preparations, so that greater comfort to the eye, patient compliance are they, stabilize the formulation, enhance the drug viability, maximize the preservative efficacy. So buffering agents that most widely used for ophthalmic also borate, carbonate, phosphate are here, like that ointment and cream. So topical product, ointment and creams also to ensure the stability of the formulation. So that most widely used citrate and phosphate buffer for the ointment, creams, like that. So that application is point of view with the pharmaceutical preparations. So like that in the laboratory part, so calibrate the pH meter for determination of pH of water, soils, etc. for the sample, to carry out various biological research in that part. In industrial preparations also, stability of ointment, cream that apply for like the skin, already we have to see. Appropriate condition for dyeing fabrics, for fermentation process in food products, so like that. So many applications are there for the buffer system or buffer solution. So that we have to see the buffer and their applications. Thank you.